Hello, hello, hello. Okay, good afternoon, everyone. I think we can talk about the lecture today. Today we will introduce deep video compression. Uh, so that in previous lectures we introduced the international standard for image compression, JPEG AI, and we also introduced the video coding standard such as H.264. Because I spent a very long time to make the H.264 program to be feasible for our experiment. So so I will assign a homework for H.264 video coding homework for you today. And today we are going to talk about the deep video compression. What does it mean, deep video compression? Here, the deep means I use machine learning method. I utilize the models to perform deep investigation about the image features. Okay, it design convolutional neural network to extract useful features for compression. Okay, we extract features so that these features can make the compression performance better. Okay, if we want to perform the image classification, then we may have to assign different features for the purpose of image classification. But now we are talking about compression, so that the model will extract features which are usable, which are good for compression. So here we will, so that the deep means that we use learning model. We did not design the modules by human. Okay, we did the machine to learn how to extract good features for the compression. And these slides are from my advisor, Dr. Xueming Han. He retired 3 years ago. So this is a slide he gave me several years ago, but I also made some modification. And this is a traditional video codec. Okay, so you should understand what is the operation logic of the video coding standard. So here, okay, this is original image, and this is a original image, and we decompose image into blocks, right? And we for the first frame, we encode the first frame as intra-coded frame, and we store the frame as this is a frame buffer. Okay. Of course, this view graph just demonstrates a video encoder framework, and because at the encoder side, we must have the reconstructed frame that can be displayed on the decoder. So in general, the encoder comprises both encoder and decoder part. Okay, so now we just repeat the same inverse transform, inverse correlation, and inverse entropy coding. Then we can get a frame at the decoder side. So the decoder is just part of the encoder system. Okay, so here we just introduce the encoder, and so if the first frame is ready, we use this first frame and second frame. Okay, this is first frame. And then we use the second frame, and we perform the motion estimation. And here we got the motion vectors, right? And then when we got the motion vectors, we can use the motion compensation to provide the predicted frame for the current frame. So here we mean that we got the predicted frame. It is x bar. X bar t is predicted frame. And then we can estimate, we can get the residual frame for the current frame. Okay, we do not intend to encode the frame as by its gray level. We just want to reduce the entropy. So here we encode the residual image. So we also perform the DCT transformation and quantization. Okay, and these signals are entropy coded, and then we can sing out the bitrate. Okay, and this is we also simulate, we also provide a decoding procedure in the encoding loop so that we can reconstruct the frame. Okay, So here, this is a predictive frame, and then this is after inverse transformation, we got a residual block. And we sum up the predictive frame and the residual block to get the reconstructed image. Okay, I think this you should understand this framework very well. Okay, so now we want to make this video codec as a deep learning version. Okay. Okay, so this view will just demonstrate that we have to estimate the motion vectors, okay, so that we can perform the differential image compression, okay, such we can reduce the entropy, reduce the signal entropy, so that the compression efficiency can be improved by utilizing temporal correlation. And this is okay, motion compensation. Okay, this is a previous frame. This is a current frame, and after motion compensation, we just use the previous frame to get the predictive frame for the current frame. Okay, here bar means the predictive frame, and then we perform the subtraction of these two of the current frame and the predicted current frame, and this is a residual frame. So we just perform compression on the residual image. Okay. Of course, the entropy of the residual image is much smaller than the original image. That is video compression logic. So again, we still have to perform the transformation, discrete cosine transform, and perform quantization. And then we also perform inverse transformation at the decoder side to reconstruct back the residual image, so that we then can sum the previous image with the okay, we then can sum up the predictive image with the residual image to reconstruct the current frame. Okay, so this is a processing logic of the video coding system. Now, what does it mean, deep video compression? Here, we use another term, end-to-end video compression framework. So what does it mean, end-to-end? End-to-end means that after the encoder receives the image, the first image, and then it output and then it reconstructs the image, all the modules inside the system are designed by deep learning method. Okay, instead of human hand design. Okay, all the modules are designed from the deep learning model. So we call end-to-end means everything is from the deep learning method instead of human. Okay, instead of human design. So that's the end-to-end means. So here we made a comparison. Okay, in the H.264 standard, you will have the homework today. We utilize the block-based motion estimation, but in the deep learning video compression system, we utilize optical flow. Of course, the optical flow, the difference between the motion estimation compensation and optical flow and warping are basically the same, but because we can utilize the deep learning model to estimate the optical flow very efficiently. Okay, we can eliminate the time-consuming motion estimation process, because the motion estimation will require 60% of the total encoding time. So, so now we can utilize the learning model. We can use a model to predict the vectors automatically, and later we will show a meta program for you to compare the difference between the motion vector block motion estimation and the optical flow estimation. And okay, now this is end-to-end video compression standard, and okay, so here we utilize the optical flow network to estimate the motion vector, and then we transform the motion vector into features. We do not compress the optical flow directly, because optical flow are different from the motion vector. In find out the optical flow, it also impose some constraint, such as a smooth constraint, so that the motion vector property are different to the block motion estimation motion vector. Okay, and after feature extraction, we perform quantization. Okay, and after quantization, we can send it to the entropy coding module. Okay, and here it just say that we use the bitrate estimation network. Here, this view graph just demonstrates the encoder system, so we have to perform training. So here we do not practically perform the entropy coding, because the entropy coding requires arithmetic coding. It is very time consuming. So at the training stage, we just use the entropy to estimate the required bitrate. Okay, so here we, after quantize the motion features, we just estimate the bitrate by calculate its entropy. Okay, instead of practical arithmetic coding process. Okay, here also here this is a residual block, and after quantization, it is sent to the entropy coding module. Of course, here this is a residual image. Okay, we also perform the subtraction between the original image and the predicted image, and this is a residual signal, residual image. And we also extract features. For example, this is a discrete cosine transform. If we compare their functions, then this can be similar to the discrete cosine transform module in the traditional video coding standard. Okay, and the quantization is the same. Okay, so that the difference is that because we have to perform training for many times, so we do not perform practical entropy coding operation. Instead, we just use the entropy to estimate the bitrate. Okay, because during the training process, we have to carry out the entropy coding for thousands of times. So we just use the entropy for the training process. Okay, so here this is just deep video compression, and here, as you can see, we after the decompression, we reconstruct back to the optical flow, and then we can we use the optical flow information to perform the motion compensation. So these are reconstructed images, and we can reconstruct, we can perform warping or motion compensation. In traditional video coding standard, we call it as motion compensation, but in deep learning system, we call it as a warping. Warping means that we just warp the current image, so that by utilizing the motion information, we can warp the image to align with the current image. Okay, we use warping in the deep learning deep video compression system. Okay, and okay, so that's the motion compensation network. It also utilizes the motion compensation network, but now it is a network. Network means that it has to learn the best parameters to perform the warping. Okay, so here this is a warping in the following slides. So this is a basic framework of the video compression standard, of the deep video compression. It is not a standard now. Okay, although I think sooner or later the deep video compression will have its international standard version. Okay, so this is a basic comparison between the deep video compression with the traditional video codec. Okay, so so this is H.265 and this is H.264. Okay, so as you can see, the H.264 outperform the H.26. Okay, this is UVG set. DVC set comprise high resolution videos, and I will show you these videos later. And so this is a DVC. This is DVC, the first deep video compression framework. Okay, so its performance is outperform H.264 only in high bit rate, but in low bit rate, its performance is still not that good as compared to the H.265. Okay, because the deep learning method has its inability to reconstruct a low resolution image very well, because in deep image compression, deep video compression, it utilizes the generating method to reconstruct the image information, so that if the change for the wait for a long time to get ready the MATLAB system. Okay, and these are proposed. These are DVC, advanced DVC method proposed by other research. But this view graph just demonstrates that for UVG set, of course, for high resolution images, the deep video compression outperform the traditional video calling standard. Okay. So this is a performance comparison between the traditional and the deep learning video compression system. Okay. So here components in learned video coding. So it has many keywords. Okay, learned video compression. Someone text is a deep video compression. Okay, but all these are their internal framework are basically the same. So here we still have to deal with intra-frame coding. Okay, so that we know that the first video coding image coding standard is JPEG, and the JPEG can perform efficient image compression. And intra-frame coding means that it does not depend on other images to perform compression or decompression. Okay, it can be reconstructed by itself. Okay, so this is it also used as an anchor frame, so that the following frame can use the intra-frame as a reference to perform motion estimation and then perform inter-frame coding. Okay, of course, in the early stage of deep video compression, we utilize the intra-frame coding method by the traditional H.265 coding standard. Okay, so we call it as a BPG. In earlier experiment, BPG, yes, BPG is intra-frame coding proposed by H.265. It is basically the same as a JPEG, but it just utilizes intra-frame coding. Okay, we have introduced that the intra-frame coding duration has been increased from 8 duration to 33 to 67, so that the BPG can provide very efficient image compression. But later, the deep video compression system developed their own image compression. So now we know that the JPEG AI has been finalized in year 2022, right? So it has been standardized. So now, of course, the deep video compression keep improve their method. So now, the deep video compression consider that we intend not to depend on the first intra-frame. So it want to eliminate the intra-frame coding, which means that the inter-frame coding will adapt to not to heavily depend on the previous frame, so that every frame can be each frame will comprise intra-block and inter-block, so that we will not use the intra-frame and inter-frame to code the video. Okay, every frame can be can comprise intra-block and inter-block. So that's the new idea about the deep video compression. Okay, and then motion estimation and motion compensation. Okay, we utilize the block. We estimate the motion vector for image block, and then we use the motion vector to perform motion compensation from previous image, right? But now we use optical flow. Optical flow, it use each pixel comprise its own motion vector. Okay, we call it as optical flow, and so that the resolution of motion has been enlarged in the deep video compression method. And we also perform entropy coding. We also encode the residual block instead of the original block. And then we also have to take good care of the motion vector compression. Okay, because the optical flow vector represent a more homogeneous or smooth motion vector distribution, so that the compression method can be different from the original motion vector in H.264. Okay, and in addition to this basic part, it also proposes refined filters, such as we introduce in-loop filter and post-processing. Okay, it will achieve the two functions, in-loop filter and post-processing, used in the traditional video calling standard. By now, we use a deep learning model to achieve the same target, achieve the same refinement target. And okay, it also utilizes the P frame and B frame, also the intra frame. Okay, the most important thing, we have to design a good loss function so that the model can learn how to ultimately encode the current image. So here is a video prediction idea. Okay, the idea of video prediction. So we use past images to predict the future image. Okay, so that we can use reconstructed images as a decoder side to predict the current frame, so that we can perform the residual compression. Okay, of course, it says that it found application in self-driving cars. Self-driving car here this is a scenario. Okay, when you are in the self-driving car, then the AI will take good care of the entire driving. So now, of course, if the camera detects that there is a person here, so it will predict the future frame. It will understand that the future for the 2 seconds later, the people will walk at this location. So that it means that we can use the motion vector or the optical flow property to generate a future frame, right? To predict a future frame. For example, the person will walk from the person 2 seconds later, it will walk toward the center of the road. Okay, so we call it as a future frame prediction. Okay, it can be used in the self-driving car, and also it will detect some buildings or some obstacles in front of the road. So it can perform some it will perform some operation step to avoid the collision or other potential disaster. Okay. So here, okay, future risk and collision prediction. Okay, we call it as a future frame prediction. Okay, but now we utilize this method. Okay, we can derive the future frame prediction in the video encoding process. Okay, in the deep video compression, because the AI can do excellent prediction. So that the challenge is that we know that the motion and appearance of the video can be highly complex. Okay, because maybe the camera is moving when the cameraman is taking the image. The camera may be in a motion status. Okay, so the object may also be moving. Okay, the object, the moving object and then maybe the object will deform itself. Okay, for example, if because humans are in a 3D world, so that after it rotates, okay, maybe I can change my viewpoint so that when the camera take my picture, then the object will be deformed because the person changed his viewpoint. So the body shape, body silhouette will be changed. So we can call it as an object deformation. And then lighting change. Okay, this is the most important thing because we know that the Tesla it just utilized the image recognition method to perform the self-driving function. Okay, it intend not to utilize any sensors, so that when the lighting condition is changed, okay, this now is a sunny day, and when in the when you drive car in the night roadside, maybe the lighting condition will change the detection result. So that is the advantage and disadvantage of the Tesla auto driving system, because it depends only on vision. It does not utilize the sensors. Okay, and some self-driving car company, they deploy many sensors, so that would be make the self-driving car very expensive. So that's why Tesla is the most popular, because it is not that expensive, because it utilizes only image feature, only vision, computer vision, to perform the self-driving function. Also, there is this occlusion. Okay, so that the motion vector is not that easy to perform efficient interframe compression, because the 3D world is captured by a 2D camera, so that many information get lost during the video capture process. Okay, so the prediction model needs to capture the motion dynamic in the temporal direction, and it still has to synthesize as clear and sharp the future video frame. So now we have to utilize the deep learning model and set up good loss function, so that reconstructing image can be clear enough and sharp enough, okay, for our human visual system. So here, this is now we have so many past frame. Okay, this is the encoder and direct generation model. So we can utilize the motion feature for this video. Okay, we get so many get so many motion vectors in the video, so that we can predict the moving of this sailing boat, right? So here we can estimate a future frame based on the past image features and the motion features to perform a prediction for the future frame. Okay, so this is the current frame, this is the future frame. Okay, so this is the main function of the human vision-based self-driving car system. Okay, it heavily depends on the prediction. Okay, predict the location of the object inside the video. So here, dense flow-based model. Okay, we know that in the traditional video coding standard, we decompose image into blocks. Okay, so that we can perform motion compensation. Okay, if this is the current image and we decompose image block, and we can get the motion compensated block from previous image. Okay, you should understand this very well. But now the motion vector in the deep video compression system is assigned for each pixel, so that each pixel will have its motion vector. So it will find the best match pixels from its previous frame. That's a major difference between the traditional block-based motion compensation and the optical flow-based we call it as a warping. Okay, so here, as you can see, the current pixel is reconstructed, is estimated from the previous frame. Okay, t plus 1 is a future frame, t is a current frame, and here is a motion vector, u and v is a motion vector, so you can get a prediction for the current pixel by the estimated motion vector or optical flow and the previous image, so that we can get a prediction for future frame. Okay, that is this approach is the same as in the motion compensation in the traditional video coding standard, right? Now, okay, so now by utilizing the correlation between the reconstructed image or the future or the past images, we can estimate optical flow. Okay, here because we can have so many motion vectors, so that the predicted motion vector for the future frame will be very perfect. Okay, because it comprise three set of motion vector map to get the prediction for the future frame. So that, as you can see, in comparison with the traditional motion estimation method, it also imposes constraint, which means that the motion vector should be smooth, so that it will not demonstrate abrupt change of the motion vector, because it imposes constraint on the nearby motion vector, nearby optical flow. They must be smooth. Okay, so it does not introduce the severe artifact that motion vector will change. Will change between nearby pixels. Okay. So here, okay, because we have the current frame, and by utilizing the motion vectors, we can perform warping. The warping is the same as the motion compensation, but in deep video compression, we call it as a warping. Okay, warping. We just warp the current frame to the next frame. So that this is just a prediction. Okay, prediction, not the reconstructed image. So here it utilizes the head as a prediction. Okay, so this is a prediction for estimate future frame. Okay, we use the head here. So as you can see from this formula, okay, when we perform the we had got to train this deep learning model. Okay, and the cost function is defined here. So the most important thing is that the estimated image should be very similar to the real frame. Okay, the real future frame. Okay. During the training process, we have set up good loss function, and here we also this is a divergence of the optical flow, so that it imposes constraint on the optical flow smoothness, so that the neighboring optical flow will not deviate too much. Okay, so that this constraint is utilized to impose the smooth constraint for the estimate optical flow, so that they demonstrate very smooth change. Okay, in the final optical flow vector map. So now we will look deeper into the deep video compression. Several research proposed new methods to improve the coding performance. And here, this is a basic deep video compression. Okay, in addition to design the framework, it also find some method to improve the compression efficiency. And the second is multiple frame. Okay, because we can get enough information to perform the prediction. For example, in this example, it utilizes past frame more than 3, more than 5, and more than 3 frames to perform the prediction. Okay, because it can extract enough features, sufficient features to perform good estimation for the current optical flow map. Okay, so it can reference more than 1 frame. okay, to perform the good prediction for the optical flow or the predictive frame. Okay, it will improve the quality of the optical flow and the predictive frame. And we can also utilize the scale space. Scale space means that when image comprise high frequency regions or disoccluded regions, okay, because we are now dealing with video, so some region may be the disoccluded region, okay, because the video comprise so many moving objects, so that when the in the moving object video, several regions can be found in the video, so we can use that scale space to deal with such a case. And here we also use the hierarchical learn the video compression. Okay, we can impose something like the GOP, group up picture, in the H.264 standard to perform the deep video compression. And here is a region adaptive, something like the in the H.265 it also utilizes motion vector merging method. Okay, for the block, okay, if the 4 block their motion vectors are near the same, then we can combine the 4 block motion vectors as one. Okay, motion vectors, so that if the motion vector are near the same, then we can utilize one motion vector for this 4 block, so that we can save the information amount by eliminate the transmission for the 3 other motion vectors. Okay, and we just transmit the motion vector, one motion vector for the 4 block, something like this one, so that we utilize this improving method in the H.265 in the deep video compression. We call it a region adaptive. Region adaptive means that in a video or in an image, we can change the resolution, or we can change the size of block that can share one common motion vector. We can change the block size, okay, so that the motion vector information can be largely reduced. So here, this is intra-frame coding. Of course, now because these papers are almost 5 years ago, we know that the so that we reserve the space for you to represent the advanced deep video compression. Okay, so that we don't introduce so many up-to-date video coding standard, deep video compression standard. Okay, so you can represent this topic in the final project presentation. Okay, and so we will introduce a detail for this video, for this deep video compression methods. So as you can see, they share the same group up picture framework as in the traditional video compression standard, because this is the earliest development of the deep video compression. So that everything is quite similar to the traditional video coding standard framework, so that they utilize the same group up picture. So they must have to encode the frame as intra, and then encode the following picture as P frame. Okay, and the only one is that the hierarchical learn video compression, and this research they propose it as a bi-directional predictive frame. Okay, so that they follow the traditional video coding framework very closely. Okay. Okay, so that the first deep video compression standard was proposed by Lu, and this is the first end-to-end learn video codec. Okay, and so it also introduced the image compression network for residual image. Okay, and optical flow coding. We have to perform the compression for the motion vector for the optical flow, and then motion estimation network. Okay, in traditional video coding standard, we utilize the block motion estimation procedure to get the motion vector, but now we use the deep learning models to estimate the vectors. Okay, so that the processing speed will not depend on the iteration. So the processing speed can be very fast. Okay, and then it's a motion compensation network. So that in terms of motion compensation network, we can call it as a warping. Okay, so that here in the traditional video coding standard, the only matrix is a PSNR, because in the traditional video coding standard, the only measurement of the quality is perfect reconstruction, so that it will compare the peak signal to noise ratio as compared to the original image, because its purpose is to perform perfect reconstruction. But now in the deep video compression standard, because we utilize the generation model to produce the reconstructed image, so that the image, the deep learning model understand how to reconstruct image content, so that they will present better, we call it as a visual quality metric. Okay, so multi-scale similarity structure index measurement. This measure is relevant to our human visual system, so that the deep learning model understand how to reconstruct images, so that the DVC always demonstrate better SSIM performance. Okay, but the traditional video coding standard H.265, H.2.266, they are very excellent in the PSNR performance, because their design target is to provide perfect reconstruction image. Okay, so here this is motion compensation network. Okay, in the traditional video coding standard, we just move the corresponding blocks in the previous frame according to the estimated motion vectors to perform the motion compensation. So that in our previous homework, you observe how the video can estimate the motion vector and then perform the motion compensation, right? So you compare so many different motion estimation methods to estimate the motion vector for each block. Okay, so that this motion vector can be used to perform the motion compensation. But now, after we estimate the vectors from the optical flow module, okay, here the V hat means that it is a reconstructed motion vector or reconstructed optical flow. Okay, because we have to perform the estimation at the decoder side, so that in the encoder side we have to provide a reconstructed motion vector to design the motion estimation module or the warping module. Okay, here this is for warping. So this is a previous frame. Okay, reconstructed frame. This is a motion vector. Okay, and so that the difference is that in traditional video coding standard, we just need to provide the motion vector and the previous reconstructed image to perform the motion compensation, right? But now here, in the deep learning model, it provides additionally a warp. Okay, so this is an initial prediction of the current frame. Okay, we also utilize the previous frame and the motion vectors to perform the warping. So here we can call this is first stage image prediction. Okay, and this is a second stage image prediction, because after warping, it will lead to some unpredicted regions or some distorted line feature. Or okay, I can show you an example. Now, okay, I have to get back to the local PC to show you this artifact. Okay, this is an optical flow demonstration, and I utilize a generative video to demonstrate the difference between the traditional motion estimation and the current optical flow estimation. Oh. Okay, the left figure shows the block-based motion estimation, and the motion vector is represented by the red arrows. But in the optical flow, as you can see, we call it as a dense flow. Dense flow means that each picture can have its own motion vector. Okay, and in addition to pixel-based motion estimation, it also imposes constraint so that the neighboring motion vectors will not deviate too much each other, okay? Because it imposes a smooth constraint on the motion vector estimation. That's the difference between the block-based and the optical flow. And okay, now we impose the optical flow on the real video to observe the difference. Video. I'm afraid that the memory may be insufficient to demonstrate this optical flow estimation program. So here I select a video, and we can observe that the optical flow property is different. Okay, so the left part is a real motion vector. As you can see, the motion vector looks like random feature, right? If the motion vector is estimate between images far from each other, then the motion vector would look very randomly. And here, because we impose constraint, so that the optical flow motions will demonstrate a more homogeneous distribution. Okay, so that's the difference between the block-based motion estimation and the optical flow, so that we can design models to better encode the optical features. Okay, this is a simple example. Okay, and then we demonstrate a third example, that what is the artifact of the utilize the optical flow to perform warping, or utilize the optical flow to perform motion compensation. Okay, so that we demo video warping. Yes, warping. I use the same video to demonstrate the warping artifact. Okay, so that, as you can see, this is the comparison. This is a previous frame, this is a current frame, and these are the motion vectors. Okay, the red arrow is represent the motion vector, block-based motion vector, and blue vector show the optical flow motion vector, right? So as you can see, the optical flow look more homogeneous because impose smooth constraint. But as you can see, this is a motion compensated video. Okay, so it suffer severe artifact, block artifact, right? This is a predictive frame, so that because we utilize the motion vectors for blocks, so that the predictive block look blocky. Okay, block artifact. But this is one video by the optical flow. So as you can see, the images are distorted. Okay, the human face is distorted very well, very badly. Okay, so that we cannot use this warp image as a predicted image. Okay, this is the first stage warp image. Of course, I use a very simple method to perform the warping, so that the the reconstructed image by using the optical flow warping maybe too bad, right? So this is the residual. So as you can see, under this condition, the motion compensated approach will provide a residual image much better than the optical flow. Okay, so this image just demonstrates that by direct warping, utilizing the optical flow and the reconstructed image, then the predicted image may look very distorted. Okay, something like a distorted cartoon video. Okay, so that direct warping is not enough, so now we have to design another model. Okay, so this is the optical flow, and so that the optical flow demonstrates the moving of the basketball. Okay, and the background is nearly static, so that there's not large motion for the background. So now this is a previous reconstructed image, and this is a motion vector. And then we perform the first warping. So the first warping image is I just showed the example that the image would look very distorted. So that we have to perform second time refinement, so that the reconstructed image can be looked more like an image. Okay, this is a distorted image, and so that we have to perform the second time refinement to generate a good prediction for the current image. Okay, so this is a warped image, this is a predicted image. So the predicted image is much better than the warping one. So here, so this is a warp image, and this CNN model here. Okay, so that this is a warp image here, and we still provide the motion vector and the previous frame, so that we can provide sufficient information for the model to understand how to generate a better image to act as the predicted image. Okay, so that everything will depend on the deep learning model. The learning model will learn how to find the optical flow, how to refine the warped frame to generate a better reconstructed image. Okay, so that this is a CNN model, and this model is just utilized because warped image itself may comprise motion vector and so in this example, it just utilizes the previous reconstructed frame and the warped image. Okay, warped image for the current frame, so that the previous frame provides sufficient information for the image context. Okay, neighboring object or neighboring region distribution, so that it provides enough information for this model to get to output a good estimation for the current image. So it also utilizes something like UNet, because if we perform the convolution and the pooling, then the image feature can be maybe smooth too much, so that they cannot have a good reconstruction. So that he used a UNet like, okay, so that the original feature detail can be reserved, so that the reconstructed image can comprise all level of features. That is the design target of this model. Okay, it utilizes CNN model, so that to act as the second stage warping procedure to provide a good estimation image for the current frame. Okay, so this is the first step to deal with warped image, to deal with the motion vector and perform a good estimation image. So here it's just explain why not use only the warp frame. Okay, here. So I just show you the example, because the warp image is not that perfect. So we still have to perform. We still have to design a refined procedure to generate the a much better predicted image. Okay, we can call it as a refinement stage. So here is the CNN refines the warp result. Okay, because the background region may become visible. Okay, because some object moving, so that it will disocclude some regions, so that it comprises many objects that is newly visible. So that the motion, so that the warping cannot generate a good prediction, because the second image comprises so many newly visible regions. Okay, so this region cannot be obtained by simple warping. So we have to perform the second stage refinement process to make the warped image more perfect. Okay, so this show time, I showed this video already. So you can click the link. Maybe later I will provide this image for you, so you can click this meta program to understand the difference between the motion estimation vectors and the article flow vector. Okay, and how can they be compressed by different methods. Okay, because the two motion vector properties are different, so we have to utilize different compression logic to compress such signals. So here this is the performance of the DVC. Okay, so as you can see, so that the dashed line shows the performance of the traditional video coding standard, and here their method demonstrates better compression performance. Okay, for the same bit rate, their PSNR is higher than the H.265. Okay, and this one is for H.26. As you can see, the H.265 outperform the H.26. Okay, but the deep learning methods in the high bit rate, their performance is nearly the same, but for the low bit rate, their coding performance, their compression performance is not that good. Okay, I think is that because the deep learning model is trained by your data set, so that it cannot provide good compression for image with different preciseness. Okay, if the model is trained to perform compression for high resolution video, then when we use this model to compress the low resolution image, the performance would be degraded. Okay, because the learning model will overfit to its training set. So if this model is trained to compress high resolution video, then it will not provide good performance when the image resolution is much lower. Okay, so it's not that easy for a learning model to provide a comprehensive coding performance. Okay, so that this is a difficult. Okay, by utilizing the deep learning model, as you can see, the operation range, this is the BPP, this is the PSNR, and this is the traditional video coding standard. The operational range is wide. Okay, when you increase bit rate, your performance, your PSNR can be improved. But for the DVC, even you provide more bits for the system, it cannot improve the compression performance better. Okay, this is a limitation of the learning model. Okay, because the learning model depends on the deep learning model will overfit to a training set, and in addition, the learning model try to compress image with different compression ratio. This is a difficult task for the learning model. Okay, because the learning model is will always overfit to the training set, or will overfit to a specific compression task. So that when we want to let the learning model to be general, it can perform good performance for different resolution images. This this is a difficult task for a learning model to achieve this target. Okay, and okay, so the first level shows the performance in terms of PSNR, right? PSNR, so it is good enough, okay, because its performance is comparable to H.265. Okay, at the year 2020, this would be a very good compression performance because it's a newly compression framework. It utilizes the deep learning model to perform the video compression. So this is good enough. And if we compare the performance by the MSSRM, okay, because the capability of deep learning model is that all images content are generated by the AI, so that the generated image will look much better from our human visual system, because in the generated video image or images, they should not comprise noise, right? Because it's a generated image, so the AI understand the content, understand how to reconstruct the image content. So in general, they comprise no noise, so that their SSIM performance will be much better. Okay, as you can see, the performance can be improved a little. For the same bit rate, the PSNR can be improved a lot as compared to this one. Okay, when we compare the database is HEVC class B dataset, and the similar performance improvement can be shown in this graph. Okay, the percentage of improvement is much higher for the deep video compression, because the AI is capable of generate video, so that their visual quality will be much better than the traditional video compression standard. Okay, of course the video would be consumed by our human visual system, so that we can consider the human visual system, human visual perception quality. This is enough. We only have to consider the visual perception quality. We don't care about the objective quality such as PSNR, okay? Because human is the only consumer of the video, so we don't care about the PSNR that much as compared to the in the traditional video compression standard. Okay, so okay, let's take a break for almost about 15 minutes, because I have to take my coffee. I dropped my coffee in my office.